and sharing my screen. And in sharing my screen, now I am, whoops, go away toolbar. Questioning, let me go to.
Yeah, the only thing that I see is Momentum Zone,
If you go into the main menu,
Flucana
grade book. Could you guys, if you're not talking to this class,
I'm not sure what I told you to cross. I don't see it on here.
When I click on review, it opens the.
So Momentum Zone and Beta Method Zone.
I'll change your attendance. Okay, so do you see how in Blackboard, if I go to gradebook?
The only thing I can say is
one of you are having a conversation outside of class. Could you please mute yourself?
Reason on why you chose these ones.
Okay, got it. Figured it out. And then if I click on review, do you see how it takes me to the questions? Can't change anything. Oh, this is a homework. The test doesn't show up for you guys?
It just says we don't have access to review it. It shows up though.
Okay, let me, after class, I'll change the settings on that. Could you please remind me to do that?
Yep, I will.
Okay, so then let me go back. Well, I guess, does anybody have questions on any homework or anything like that? If not, today we're going to, move on past the preliminary chapter. We're going to start looking in chapter 1. Chapter 1 involves solving a variety of equations. Before they go through and do that, though, they do introduction to the Cartesian plane. So today we're going to look at Cartesian plane. Then we're going to look at solving first degree linear equations in one variable. And then we're going to possibly, if there's time, start also looking at solving rational equations. Homework 1.1 and 1.2 are due on the 4th. I would have them due on the 2nd, next Tuesday. However, are you folks aware that there are no classes next Tuesday? Was that something you guys were aware of or no?
I did not know that.
It's something used to be called CCI Day. It was a day where the campus was open for high school students to come in and different programs did different demonstrations. When last I asked, they couldn't tell me what was scheduled for that day, but I'm just double checking now. I know that in talking to the head of my division, they had said that they had no idea what was scheduled for that day, but I'm looking at the academic calendar right now, and it does show Tuesday, March 2nd, they call it an all-purpose day, and they say there are no day or evening classes. So there will be no classes on the 2nd. I guess because we're doing this virtually, if you guys wanted to, we could still meet, but I'm going to go on the assumption you'd probably appreciate a day off.
Yeah.
Yeah. Okay, then we'll plan on not meeting. So let's start looking at this section 1.1 and start talking about the Cartesian plane. Are any of you familiar with the Cartesian plane? Have any of you heard of it before?
No.
I'm guessing that when I draw it, you will be very familiar with it, and you're just not familiar with this name for it. If I were to draw the Cartesian plane, I would draw something that looks like this. Is this picture familiar to everybody? It's also referred to as the coordinate plane.
That sounds more familiar for me.
It's called the Cartesian plane because it's named after Rene Descartes. And has anybody taken any philosophy classes? Rene Descartes was a famous philosopher, but also a famous mathematician. And if you ever get a chance to look at all that math history, it's really fascinating because an awful lot of what is done in math was initially done by people who were also philosophers. And it was much more an exercise in reasoning than in practical applications. And it was only after time that an awful lot of these things developed applications. So, math initially was almost much more a thinking logic type of exercise than actually, practical applications. Most of when I studied math history, a large bulk of what I saw was, of course, European mathematicians, but there's also significant contributions from all sorts of different societies and cultures. And again, a lot of it was just kind of, even in geometry and things like that was just kind of developed as reasoning. So anyways, the Cartesian plane is named after Rene Descartes, who was one of those mathematicians. So it's the coordinate plane. Now, if you were to describe to me what the coordinate plane is made up of, what would you tell me?
Axes, I guess, to start.
Okay, except instead of axes, the plural is axes.
Yeah.
There's one that's horizontal, which is the x-axis. And there's one that's vertical, which is the y-axis. And what they really are just number lines, that came out wrong, sorry, that are perpendicular. And they have a common zero, so that they intersect at a common zero. And so the x-axis, because it's a horizontal number line, as we go to the right, it's positive. As we go to the left, it's negative. Y-axis, as we go up, it's positive. As we go down, it's negative. And they're used to locate points. Let me put a couple more numbers on these so we have a little bit more ability to locate points. So let's locate point A, and let's give A the coordinates 3, 1. And again, when I first learned this many, many moons ago, it was like before people used GPS to get around. And has anybody ever looked at an old-fashioned map, tried to locate someplace, and there's one that's letters and one that's numbers, and they give you that pair to locate your where you are. And so we locate points. And you know what I forgot to add? Using ordered pairs. Ordered pairs x, y. The x is called the abscissa, and the y value is called the ordinate. And so if I go to the point 3, 1, the x value is 3, so I go to 3 on the x-axis, 1 on the y-axis. And if I were on graph paper, you could see that that grid would intersect there, and that would be my point A. Instead, if I had a point B, which is, let's make B the point -2, 4. So I'd go to -2 on the x-axis, 4 on the y-axis, and we'd see the grid intersects here. instead, if I put point C here, what would you tell me the coordinates of C are? If C is, the X value would be 0, and the Y value would be -3. Are you folks comfortable plotting points?
Yes.
Yes. That assignment 1.1 has a lot of, locating points and identifying coordinates in it, in addition to some of the other stuff we're going to do in a little bit. So the axes also divide the plane into regions. There's actually 5 regions. There are 4 quadrants. And then the 5th region is on the axes. So when I look at the 4 quadrants, I start with the first quadrant over here where both X and Y are positive. And then I go around in a counterclockwise direction, 1, 2, 3, and 4. And we'll notice later on when we look at trigonometry why it goes in a counterclockwise direction. But a brief summary, we can think of angles as being drawn with one side on the x-axis and the vertex, the angle at the origin. And we say that as angles open upward, they're positive. And as they open upward in that standard position, they will go around in that counterclockwise direction. So it's kind of like we're moving the hand of a clock in that counterclockwise direction. It has positive angles. One last definition that I want to put in. Has anybody heard of the origin?
Yes.
And the origin is the point, we'll call it O, and its coordinates are 0, 0, and it's that point of intersection. So far, so good. Any
Mhm.
questions?
Nope.
Then I'm going to turn the page for a minute and talk about an equation just for a minute in 2 variables. And if we have an equation in 2 variables, a solution is an ordered pair whose coordinates satisfy the equation, make the equation true. So what's that all about? If I look at an example, an equation in 2 variables might be 2x plus 3y equals 1. And I might be asked, is 1 negative 1 a solution? And we check by substituting. If I've got the point 1, negative 1, we'd substitute x equals 1, and the y value, y would be negative 1. So that gives me 2 times x is 1, plus 3 times y is negative 1. And we want to know, does that equal 1? Simplifying, I get 2 minus 3, or negative 1. Ooh, that does not equal 1, so my answer is no. Same equation. What if I asked, is negative 1, 1 a solution? Well, this time, x would be negative 1 and y would be positive 1. And so in my equation, 2x plus 3y equals 1, I'd have 2 times negative 1 plus 3 times y is 1, which would give me negative 2 plus 3, which is 1, equals 1. So the answer is yes. But what's interesting, let's try another one. Is 2, -1 a solution? And so this time in that 2x plus 3y equals 1, I'd have 2 times x is 2, 3 times y is -1. And I want to know, does that equal 1? Well, that would be 4 minus 3, or 1 equals 1. So it also checks. And you see that we can have many solutions. We can have more than one solution. And it turns out that we can have an infinite number of solutions. Not always, but it's possible that an equation in 2 variables can have an infinite number of solutions. And so we look at the graph of an equation. And it's going to be the set of all the points whose coordinates satisfy the equation. So that the graph of an equation is a set of all the points whose coordinates satisfy the equation. And so that gets us into some of the other problems that you're going to see in this homework 1.1. And that's where we're going to be sketching the graph of an equation. Is everybody all right if I turn the page, or do you need for me to wait a minute? We good?
Can we wait just 1 minute? I'm finishing the last sentence.
Gives me a tea break. Ready?
Yep, thank you.
Okay. And as we look at this, I'm hoping that this is familiar territory for folks, but on the off chance it isn't, I'm going to look at a couple of examples. We're going to sketch the graph of an equation. And oh no, we're not going to be using a graphing calculator. We're going to sketch them by making a table of values. Then plotting the points. And so I'd like to look at 3 examples that are maybe a little bit different. First example, we're going to sketch y equals 4 minus x squared. And for the table, we'll use x is -3, -2, -1, 0, 1, 2, and 3. Would I make a table of values and make a table with 3 columns? Obviously, the middle one is wider. The first one will be my x values. The second in the middle, I'm going to write my equation, y equals 4 minus x squared. And then in the third column, I'm going to put my y values. So first x value is -3. So now I'm going to substitute that -3 in for x. Remember, use your order of operations. -3 squared is 9, and then 4 minus 9 would be -5. Then when x is -2, y would be 4 minus -2 squared, which would be 4 minus 4 or 0. When x is -1, y would be 4 minus -1 squared. 4 minus 1 would be 3. When x is 0, y would be 4 minus substituting in 0 squared, which is 4. When x is 1, y would be 4 minus 1 squared, which is 3. When x is 2, y would be 4 minus 2 squared, which is 0. And when x is 3, y would be 4 minus 3 squared. 4 minus 9 would be 5. Please notice when I substitute in those negative numbers, especially because I'm squaring them, raising them to a power, I put parentheses around the value. Now, we're going to look at those ordered pairs as points and plot them in the plane. When you do a graph by hand, please make sure you label your axes, X and Y. Make sure when you scale them, you try to keep the spacing consistent on your axes. And so the first point is -3, -5. The second point is -2, 0. Then the next point is -1, 3. Then I have the point 0, 4. Then I have the point 1, 3. The point 2, 0. The point 3, -5. And then I'm going to try to connect them with a smooth curve. And then I'll label the graph with the equation y equals 4 minus x squared. And we'll find out next unit when we spend more time graphing that we should recognize that this would be a curve because there's an exponent on x. When we look at a graph, one thing that we have a tendency to focus on is something that's called the intercepts. And the intercepts are the points where the graph crosses the axis. And that should have been axes, not axis, plural. We talk about the y-intercept, which is a point on the y-axis. And if I go up and look at this graph over here, my y-intercept would be this point. And because it's on the y-axis, won't its x value, its abscissa, always be 0? So here it would be the point 0, 4. But the y-intercept will always have an x value of 0. It'll be a point of the form 0b because all of the points on the y-axis have an x value of 0. Similarly, if I look for the x-intercept, it's going to be a point or points on the x-axis. And so if I look at this graph, you see here we have two x-intercepts. This one would be the point +2. And doesn't it make sense that if it's on the x-axis, the y value will be 0? And this one would be the point -2, 0. And so they'll always have a y value of 0 or be a point of the form a0. And so your intercepts are where you cross the axes. If we're on the y-axis, the x value is 0. If we're on the x-axis, the y value is 0. That one, all right. Any questions? Can I turn the page? Not hearing any complaints? Let's look at another example. This time, let's sketch y equals the absolute value of x minus 1. And let's use for the table x equals -2, -1, 0, 1, and 2. So again, I'm going to make my table of values. X, y is the absolute value of x minus 1. I'm going to find y using -2, -1, 0, 1, and 2 for x. So when x is -2, y is the absolute value of -2 minus 1. Well, the absolute value of -2 is +2. 2 minus 1 is 1. When x is -1, the absolute value of -1 is 1. So substituting in the absolute value of -1 minus 1 would be 0. When x is 0, y is the absolute value of 0 minus 1, which would be -1. When x is 1, y is the absolute value of 1 minus 1, which is 0. And when x is 2, y is the absolute value of 2 minus 1, which is 1. Is everybody comfortable with that table of values? If so, I'm going to plot those points by drawing first my axes, putting a scale on them. First point would be -2, 1, then -1, 0, then 0, -1. And you notice this time they're kind of falling on this straight line. But then the next one is 1, 0, and then we have 2, 1. And so that's also a straight line. And we get this very distinctive V shape. And we'll find that if we look at an absolute value graph very frequently, it will have this distinct V shape. If I ask for the y-intercept, what would you tell me it is?
Zero, -1.
And if I ask about x-intercept, what would that be?
-1, 0, and +1, 0.
Beautiful. Everybody all right with making a table of values, substituting in, and then plotting the points? Have you
Yeah.
all had to make a table of value by hand? I know it frightens me that on occasion I've got students that have never done that by hand. They've always just gotten that table of value off a graphing calculator, which is crazy. Everybody all right with that?
Yeah, I'm okay.
I'd like to look at just one more example then. And this time let's sketch y equals 1 over x, or y is the reciprocal of x. And this time let's use for x values -2, -1, -1/2, -1/3, 0, 1/3, 1/2, 1, and 2. So I'm going to make my table with the column for x, the equation is y is 1 over x, and then a column for y. And so when x is -2, y is 1 over -2, or -1/2. When x is -1, y is 1 over -1, which is -1. When x is -1/2, y is, gosh, this looks ugly, 1 over -1/2. But again, that means taking the reciprocal. So that would give me -2. And when x is -1/3, y is 1 over -1/3, or the reciprocal of -1/3 is -3. What happens when x is 0? What happens when I take 1 over 0? Can I take 1 over 0?
No.
No, so that's going to be undefined. Cross it out. And then on the other side, if I look at 1/2, if y is 1 over 1/2, the reciprocal of 1/2 is 2. I'm going out of order. 1/3, y would be 1 over 1/3. Reciprocal of 1/3 is 3. 1, y would be 1 over 1, which is 1. 2, y would be 1 over 2, which is 1/2. When I draw my axes, I'm going to just label the whole numbers and kind of wing it for some of those fractions in between. At -2, it's -1/2. At -1, it's -1. At -1/2, it's -2. At -1/3, it's -3. And it has no value at 0, so we're never going to touch the axis. But as I look at this graph, if I connect it with a curve, you see how this is going to get lower and lower and lower and get close to the axis, but never touch it. And in the same way, this one's going to get higher and higher and higher and get close to the axis, but never touch it. Then on the other side, at 1/2, it's 2. I skipped. At 1/3, it's 3. At 1, it's 1. At 2, it's 1/2. It's kind of doing the opposite thing. As it gets closer to 0, it's going to get higher and higher and higher and approach the axis, but not touch it. And then as it gets larger, it's going to get closer and closer and closer to 0, but never quite equal 0. And so I wanted to look at this graph because this is an example of a graph that has no y-intercept. It never touches the y-axis, and also no x-intercept. It never touches the x-axis. So not all graphs have intercepts. And we might run into some that have an x-intercept but no y. We might run into some that have a y-intercept but no x's. In addition to finding those intercepts by looking at the graph, you will have some questions that ask you to just find the intercept without a graph. And so let's look at an example like that. Let's find the x and y intercepts of, let's look at 2x minus 3y equals 6. And so first, to find the x-intercept, then we had said that the x-intercept is a point on the x-axis. And all of those points have a y value of 0. So we'll substitute y equals 0 and solve for x. So 2x minus 3y equals 6 would be 2x minus 3 times 0 equals 6. Well, 3 times 0 is 0. 2x minus 0 is 2x equals 6. And so we would get x equals 3. So my x-intercept is the point x value of 3, y value of 0. And again, similarly, to find the y-intercept, it's on the y-axis. All the points on the y-axis have an x value of 0. So we'll substitute x equals 0 and solve for y. So with the same equation, 2x minus 3y equals 6. To find the y-intercept, we'll put in 0 for x. 0 minus 3y would be negative 3y equals 6. And then dividing, we'll get y equals negative 2. And so my y-intercept isn't just really that number, but it's a point. It has an x value of 0 and a y value of negative 2. And how does that look? Everybody comfortable? Any questions? Do I need to wait a minute or are we all in the same place?
Can I just get a moment, please?
And if I'm talking too fast, please yell at me.
All right, I'm good, thank you.
So if these ideas are all right, that's what's involved in that homework 1.1. So let's move on and look at what's in section 1.2, and that deals with solving linear and rational equations in one variable. And so when I talk about a linear equation, I'm referring to a first degree equation. And hopefully everybody remembers that the degree of an equation is the highest exponent. So the highest exponent on my variable will be 1. And again, we don't write that exponent of 1. If I look at a linear equation in one variable, it'll have a general form that looks something like ax plus b equals c. Here, x is my variable. A, b, and c will be real numbers. We'll be looking for a solution, which will be a value that makes the equation true when we substitute it in for the variable. To do this, we want to take that general equation and we want to transform it into the form X equals D. And in order to do that, we need to use our properties of equality.
What you doing, Smoosh? Taylor.
Any questions? If not, I'm hoping that these properties of equality look very familiar. So I'm going to be a little bit lazy and write them symbolically instead of in words. The first is the addition property of equality. And it says if I have an equation, something like A equals B, then A plus C will equal B plus C for any number C. So I can add the same thing to both sides of an equation. And if I do it to both sides of the equation, it remains true. So if I look at an example, if I have something like X minus 2 equals 5, and I want to solve for X. To solve for X, I want to transform it into an equivalent form where the X is alone on one side of the equal sign. And in order to isolate the X to get it alone, I have to do something with the minus 2. Well, the opposite of minus 2 is add 2. And by what we just said, it'll stay equal if I add that same quantity to both sides. I'd like to make sure I put that equal sign in between to make sure that I am doing the same thing once to both sides. I've seen a lot of people make careless mistakes by not doing that, where they add the same thing to one side multiple times and never the other. I like putting those equal signs in and lining them up. And that would leave me with X plus 0 equals 7, or X equals 7. Special case of addition would be adding negative numbers, which would be the subtraction property of equality. And that would be, if I have an equation, something of the form A equals B, then I can subtract the same thing from both sides for any value C. And again, it's really just a special case of that addition property, because we can look at that subtraction as if we were adding a negative number. If we look for an example of when I might use that, let's say I've got Y plus 6 equals negative 4. And again, my variable this time is Y. I want to isolate the Y. I want to transform it into an equation where it's Y equals a number. To get the Y alone, we'd have to do something with that plus 6. But the opposite of adding 6 is subtracting 6. So we'll subtract 6. So I guess technically what we're doing here is using that additive inverse property, knowing that those opposites add to 0, would leave me with just on that left-hand side Y, and on the right-hand side, Y would equal negative 10. With me so far, folks? I'm guessing you can guess then the next place we're going is the multiplication property of equality. And that says if two quantities are equal, I can multiply both sides by the same number and it will remain equal. Here, though, we want to specify that C is not 0. I guess technically, if we multiplied both sides by 0, it would still be equal, but we'd end up with 0 equals 0, and we'd totally eliminate the variable. So you want to make sure that you never multiplying through by 0. When we look at rational equations, a little bit later, we'll see that that's where some of those things called extraneous roots come from. So if I look at an example, go ahead. Question? Let's look at an example. Let's look at 2/3 x equals 4. For those who aren't here, I want to rewrite the equation so people can see what we started with, because here when we multiply both sides by the same thing, it ends up looking a little bit different. We want to transform this into an equation that's x equals a value. When I look at this x equals a number, that x has a coefficient of 1. And so we want to go ahead and get a coefficient of 1 here. And so to get that coefficient of 1, we need the multiplicative inverse. So we're going to use the multiplicative inverse. So we'll multiply both sides. And I'm sorry, I didn't show it on the second side yet. By the reciprocal. And we'll look at that a little bit more in a few minutes. But over here then, 3/2 times 2/3 is 6/6 x or 1x. This product would give me 12/6. I'm sorry, 12/2. And so I'd get x equals 6. And then lastly, if we look at the division property of equality, it says that if I have an equation, if A equals B, I can go ahead and divide both sides by the same quantity and it remains equal as long as what I'm dividing by is not 0. So to look at an example here, if I have 5x equals 2, again, what we want to do is we want to get a coefficient of 1 on the x. So to change that 5 into 1, you have to divide by 5. And again, if we divide one side by 5, we have to divide both sides by 5. And so we get x equals 2/5. And again, you're going to find, I know some semesters I've had people get very mad at me for the number of questions that have fractions as answers. Think about how many integers there are, and then remember between any two integers there's an infinite number of fractions. So there's way much more fractions than there are integers. So don't be surprised if you get integer answers. With these in my math lab, they'll ask you to express your solution as an integer or the ratio of integers. And that means they want a fraction, not a mixed number, not a decimal, but a fraction. So if you see that phraseology, realize that your answer should be a fraction. Is it all right if I turn the page, or do you guys want me to wait for a minute?
I'm okay.
And if there are no questions, we're going to just then go through what is the normal approach that people take to solve a first degree linear equation. And usually the first thing that you want to do is you want to simplify each side. Before you start doing anything, look at each side of that equation and make sure that each side is simplified as much as possible. I know usually when I teach the calculus class, the number of times I say, if you simplify first, it's called simplify because it makes your life simpler. Then we're going to use the addition or the subtraction property of equality to get all the variables on one side of the equation. And then after we get all of the variables on one side of the equation, we're going to use the addition or subtraction property to get all the constants on the other side of the equation. And remember, those constants are your plain old numbers, the numbers without a variable attached. Then, after we've got all of the variables on one side and all of the constants on the other side, we use multiplication or division property to get a coefficient of 1 on the variable and then we'll end up with an equation where it's x equals a constant. Last step is we always want to do a check by substituting into, we always want to substitute into the original equation. Everybody all right? Can I turn the page? Look at some examples.
Yep.
Actually, let's pick this first example down below. Let's look at 6x minus 3 equals 63. First of all, I'm going to look at that left-hand side. And does everybody see that's as simplified as it can be? What I've got are two unlike terms. If I look at the right-hand side, there's just a constant there. And so that's simplified completely. Now I look, and the variable is already just on one side. So I don't need to move the variables together. So then I'm going to take this constant term and move it to the other side by adding the opposite. So the opposite of minus 3 is positive 3. And again, I like to make sure that I line up the equal signs. And this way I think to myself, negative 3 plus 3 is 0. So I'm left with 6x equals 66. Now that that variable term is alone on one side, all the constants are on the other. To get that leading coefficient to be 1, we're going to have to divide both sides by 6. Here's 6x divided by 6 would leave me 1x or just x. And then on the other side, 66 divided by 6 is 11. And when I do my check, I always want to go to that first equation that I was given. I want to substitute my value for the variable and see, does that indeed give me, satisfy the equation? So 6 times 11 would be 66. 66 minus 3 is 63. And it checks. And that equation wasn't too bad. Let's look at a few more with increasing degrees of difficulty. Next example. Let's look at 5x minus parentheses 2x minus 10 close parentheses equals 35. Here in this one, and again, I'm going to rewrite the equation to show my work on it, that we can simplify what's on the left. Order of operations, I start in parentheses. They're not like terms, so I can't combine them. So to take them out of parentheses, remember for subtraction, and put that 1 in there, and then I distribute that -1. So I get 5x minus 2x, and then -1 times -10 is plus 10 equals 35. Now I can simplify further because I have like terms. So that gives me 3x plus 10 is 35. Again, with this equation, my variables are all on one side already. So now I want to, from that side with the variables, move the constant. The opposite of positive 10 is -10. So I'll either add -10 or subtract 10 from both sides. Here, plus 10 minus 10 is 0. So that leaves me with 3x plus 0, or 3x. And on the other side, 35 minus 10 is 25. And then to get that coefficient of 1, I'm going to divide both sides by 3, and I get x equals 25/3. And again, the majority of the time, they're going to ask you to express it as a ratio of integers, which means they want you to leave it as that fraction. Do not worry about changing that into a mixed number, and do not worry about changing that into a decimal unless you are told to. Next example. Let's look at 2 parentheses 2x minus 1 close parentheses plus 3 is equal to x minus I apologize, I miswrote, x minus 3 parentheses x plus 1. And here, with this one, does everybody see that I need to simplify what's on that left-hand side? In parentheses, I can't combine, there are no like terms. So I'll start by distributing the 2, 4x minus 2 plus 3. And now I can combine these like terms to get 4x plus 1. Now that left side is simplified completely. On the right-hand side, be careful. I'm not just distributing 3, but I'm distributing the entire quantity -3. So that gives me x. -3 times x would be minus 3x. -3 times 1 would be minus 3. And so x minus 3x is -2x minus 3. Now both sides are completely simplified. And so this time we do have a variable on both sides. And so we want to use either addition or subtraction to move all of the variables to one side. It doesn't make a difference which side you move them to. It's been my experience, though, that people are usually like positive numbers better than negative numbers. And so to get a positive coefficient, I would add the smaller term. And so obviously -2 is much smaller than +4. So I'm going to add 2x, add the opposite to both sides. Here I'll get 6x plus 1 minus 2x plus 2x is 0. Minus 3 would give me -3. Then to get the x term alone, I need to move that constant constant, pardon me, +1. The opposite is -1. So I'll add -1 to both sides. Because those are additive inverses, they'll add to 0, leaving me with 6x plus 0, which is just 6x. And on the other side, I'll get the sum of -4. And then finally, to get a coefficient of 1, to turn 6 into 1, I have to divide by 6. That leaves me with 1x, or just x. And that fraction reduces to -2/3. And so that would be my answer. How are those examples? Any questions? If not, next example, I'm going to have 5x plus 9 equals 9 times x plus 1 minus 4x. And I'm going to wait a minute and ask you folks to work on this one, please. With this one, did everybody start? I can't simplify the left-hand side by trying to simplify the right-hand side by distributing that 9 to get 9x plus 9 minus 4x. And then I can simplify, pardon me, that side more by combining like terms. 9x minus 4x is 5x. And now I have variables on both sides. So the opposite of 5x is -5x. I'm going to add that to both sides. And when I do that, I get 9 equals 9. And so I notice, first of all, that there's no variable left. And if there's no variable left, I want to look at the resulting equation. I'm going to ask, is that true? Does 9 equal 9? And I hope everybody says yes. And so this equation is an example of an identity. So if there's no variable left, and the resulting statement is true, an identity is an equation that's true for all values. No matter what you substitute in, it will be true. The solution set is the set of all real numbers. So if it's an identity, it's always true. And the solution set is all real numbers. Instead, let's look at another example. Let's look at 3 times 2x. I'm sorry, 3 times, I apologize, x plus 2 is equal to 7 plus 3x. So simplifying what's on the left, first I'll distribute and get 3x plus 6 equals 7 plus 3x. Then I want to gather all of the variables together on one side of the equation. To move the 3x, I'll subtract 3x from both sides. Again, I want to line up those equal signs to make sure I am doing it to both sides. 3x minus 3x is 0, plus 6 is 6, equals 7. 3x minus 3x is 0. 7 plus 0 is 0. So here there's no variable left. But this time, is it true? Does 6 equal 7? And there I get a definitive no. And so this is an example of an inconsistent equation. And an inconsistent equation has no solution. The solution set is the empty set. And to show that it's empty, we can have braces with nothing in it, or we can have that 0 with a slash through it, which is the null set. And so sometimes when you're solving equations in my labs, you're going to see that they give you a choice. It's going to have those little radio bullets, and it's going to give you the equation. And when you go ahead and solve the equation, there's going to be, and actually, let me make sure, let me pull up right now. I'm taking a minute to pull up a question from the homework to make sure that I'm not misspeaking. And so with these, I want to give you the exact wording that my labs is going to give you. When you go through and solve an equation, they'll give you choices. They'll give you a circle that you can pick A, the solution set is. And you'll type your answer in there. They'll give you B, the solution set is, and they have the set of all x such that x is a real number. And you'll use that if your equation is an identity. Or they'll give you C that says the solution set is the empty set. And that's what you'll use if you have an inconsistent equation. So if, like those first several examples that we did, you get an answer, you're going to just type your answer in here. If, like that very last problem, we found that there is no solution, we pick this one. Or if, like the example before, we got that it was always true and the solution is all real numbers, we pick this one. And so when you see those choices, they're asking you, do you get a solution? Are all numbers a solution? Is your equation an identity? Or there are no solutions. The equation is inconsistent. You get a false statement. Is everybody all right with what those three choices will mean in the homework? If so, next we're going to look at linear equations. With rational coefficients. With rational, I apologize, coefficients. And so I'd like to look at an example. Let's look at 4/3 x plus 1 equals 9. And with an equation like this, I would probably just deal with the fraction. I can't simplify what's on the left. I can't simplify what's on the right. There's only one variable, so I'm going to move that constant term by subtracting 1 from both sides. That would give me 4/3 x plus 0. I don't need to show that addition by 0 is equal to 8. And then here, again, we spoke in order to get that coefficient to be +1, we want to multiply by the reciprocal of the coefficient. And so the reciprocal of 4/3 is 3/4. And so we'll go ahead and multiply both sides by 3/4. Here, this would give me 12/12, or 1x equals, here I have 24/4, or 6. Is everybody comfortable with that idea that if I just have a single fractional coefficient, I can multiply in that last step by the reciprocal of that coefficient? Next example is a little bit dicier. Let's say I have x over 5 minus 1/2 equals x over 6. And we could just go ahead and do the arithmetic with the fractions on this. But is there anybody in the room who's not a big fan of fractions? Fraction, addition, subtraction, and so on. Because there's another approach that we can take, and we can eliminate the denominators by first finding the least common denominator of all the fractions. And so here, the least common denominator would be between 5, 2, and 6, I believe would be 30. Then we're going to multiply both sides. You can use that multiplication property of equality. We're going to multiply both sides of the equation by that least common denominator. And we'll sometimes have to distribute if needed. And so what does that look like? On my left-hand side, I've got 5x minus 1/2, and I want to multiply that side by 30. On my right-hand side, I have x over 6, and I want to multiply that side by 30. On the left, does everybody see the need to distribute? So that's going to give me 30 times x over 5 minus 30 times 1/2. And, well, if I think this is being 30 over 1, 30x divided by 5 is going to be 6x minus, if I multiply here, I get 30 times 1 over 2, which is 15. And on the other side, I've got just that x over 6 times 30. I think of that as 30 over 1. I get 30x, pardon me, over 6, which would just be 5x. And how does this equation look like compared to the original equation? Most people would much rather solve that derived equation than the original equation. So now let's go and solve that resulting equation. Let's see, to solve that, I want to get all the variables together. Since this side has a constant and this one doesn't, I'll subtract the 6x from both sides, giving me negative 15 equals negative 1x. I want that coefficient to be +1, not -1. So I'll divide both sides by -1 and get x equals 15. And so now with this one, let's look at the check because we want to check in the original. And that original was x over 5 minus a half is equal to x over 6. If I take 15 over 5 minus a half, that would
Rajudai.
something wrong? Do you have a question, Zach? So then 3 minus a half would be 2.5 would be 5/2. And over here on the other side, when I substitute 15 over 6, that would be both divisible by 3 reduced to 5/2. And I've got it. And so how does that approach look if an equation is full of fractions? To eliminate those fractions by multiplying both sides by the least common denominator. Everybody all right? If so, we're going to jump from these linear equations in one variable and start looking at rational equations. And when I look at a rational equation, I'm going to talk about an equation that has a variable in the denominator. And so an example might be something like 5 over x is equal to 10 over 3x plus 4. And just like when we were looking at simplifying rational expressions, we have to determine restrictions on the variable, find what values to exclude. And again, where we have to exclude are values that make the any denominator equal 0. We have to remember that that denominator cannot equal 0. And so we'll set each denominator equal to 0, solve, and exclude the results. So as I go through and look at this equation, it's got two denominators. One is x. So when I set x equal to 0, well, there's no work in solving that. So we know that x cannot equal 0. And then if I look at setting that next denominator, 3x to 0, I guess to solve, we'd have to divide both sides by 3, which would also give me x equals 0. So x cannot equal 0. So we're going to exclude 0. My solution cannot be 0. Then we're going to approach it the way we did that last equation. where we had denominators, but they were just numeric. But we're going to do something very similar here. We want to find the least common denominator of all the fractions. And remember, that turns out to be the product of the factors of each denominator. Uncommon factors. We use the highest exponent. So here, I'm going to rewrite the equation 5 over x equals 10 over 3x plus 4. Well, for my lowest common denominator, each denominator looks factored already. I need a factor of x. I need a factor of 3x. The highest exponent on x is 1, so that'll just be 3x to the first. Then we're going to multiply both sides of the equation by that least common denominator. We're going to distribute if necessary. And then simplify what we've got. So again, going back to my original equation, 5 over x equals 10 over 3x plus 4. My common denominator is 3x, so I'm going to multiply both sides by 3x. On the left-hand side, if I look at is 3x over 1 times 5 over x. I can cancel those x's out, and that leaves me with 15. On the right-hand side, when I distribute, I get 10 over 3x times 3x over 1 plus 4 times 3x. Here, the 3x's cancel, and I'm left with 10 plus 4 times 3x would be 12x. And I said 12x and I didn't write 12x, I apologize. Now we'll solve that resulting equation. So to get the variable alone, it's only on one side, so I'll subtract the constant 10 from both sides, giving me 5 equals 12x. And then to get that coefficient of 1, we'll divide 12 by 12, and we'll get x equals 5/12. And we want to check in the original, and at its very minimum, we want to make sure we have no extraneous roots, which would solve the original, the derived equation, but not the original equation. We want to make sure that the solution is not an excluded value. And so I'm checking in 5 over x equals 10 over 3x plus 4. I'd have 5 over 5/12 equals 10 over 3 times 5/12 plus 4. Well, let's see. 5 over 5/12 would be like 5 over 1 dividing by 5/12 would be like multiplying by 12/5. So that leaves me with 12. Here, 10 over, if I multiply, that would be 10 over 15/12, which would be 10 divided by 15/12, or 10 times 12/15, which would give me 120 over 15, which would be 8 plus 4, and 12 equals 12, so it checks. What do you think? Shall we try a couple more? Can I turn the page?
Yep, that'd be good.
Next example. Let's look at 2 over x minus 2 is equal to x over x minus 2 minus 2. So let's start again by looking at our restrictions. The denominator, they're both x minus 2. Well, if that equals 0, solving that equation gives me that x would be 2. And so my restriction is that x cannot equal 2. So far, so good.
Yes.
Between the fractions, does everybody see they already have a common denominator, which is x minus 2? So I'm going to take both sides of that equation and multiply them by x minus 2. On the left, where I take x minus 2 over 1 times 2 over x minus 2, with what we did with the product of rational expressions, does everybody see those x minus 2s would cancel? And I'm left with just 2. That side looks better. On the right-hand side, we've got to distribute. So I'd have x over x minus 2 times x minus 2 over 1 minus 2 times x minus 2. Product of the fractions, the denominators would cancel, leaving me with x. And then over here, distributing, I'd have minus 2x plus 4. Now combining like terms, on the right, x minus 2x would give me negative 1x plus 4. Now to get the variable alone, let's subtract 4 from both sides, giving me negative 2 equals negative x. Almost there. I don't want to know what negative x is. I want to know what 1x is. So I'll divide both sides by negative 1. And that gives me x equals 2. Uh-oh. Uh-oh. Didn't we have a restriction? my restriction was that x cannot equal 2. And so we're going to say that this equation has no solution. So let's look at one more example. Is everybody all right with this one? Not hearing any complaints, let's look at 3 over x plus 3 is equal to 5 over 2x plus 6 plus 1 over x plus 2. So first I'm going to ask you folks to tell me what the restrictions are. I'll give you a minute to find them. Did everybody get that x cannot equal -3 or -2?
Yep.
Then next thing we have to do is find the least common denominator. First denominator has a factor of x plus 3. That second denominator, does everybody see that that second denominator can factor? There's a common factor of 2, giving me 2x plus 3. And so I need to add a factor of 2. And then that third denominator is x plus 2. And so this time my common denominator is quite a bit more involved. It's 2 times x plus 3 times x plus 2. So let's have you folks all go through and multiply both sides of that equation by that common denominator. And I'm going to leave that denominator in factored form. Distribute that out. And tell me what your resulting equation looks like. I'll give you a couple minutes. Just looking in, I realized that I copied the problem a little bit differently than what I had original, but that's okay. This is real solvable. Did everybody get simplified? 6x plus 18 equals 7x plus 16. Does anybody want any details provided in between? Or could you all get there? Are we good?
Yeah, I'm just checking over your work really fast, seeing how you got this.
Okay, well, now I can go through slow motion instant replay.
Okay.
The common denominator is that 2 times x plus 3 times x plus 2. Is that part all right for you?
Yeah, that's okay for me.
So then I'm going to take that and multiply both sides by it.
Hmm.
On the left, when I multiply by the 3 over x plus 2, those x plus 2's are common factor. And so I'm left with 2 times x plus 3 times 3, or 6 times x plus 3, which would give me 6x plus 18. Is the left-hand side okay?
Yeah, that's fine.
Then on the right-hand side, it's a pain in the ass to distribute. But it's really just taking that common denominator and multiplying, showing it next to each term. Here, the 2x plus times x plus 3's cancel. So in that first part, I'm left with 5 times x plus 2, which would be 5x plus 10. The second part, the x plus 2's cancel. So I'm left with 1 times 2 times x plus 3, or 2 times x plus 3, which is 2x plus 6. That okay?
Yeah, that's okay.
And so now when I combine like terms on the right, I've got 7x plus 16.
Okay. Yeah, thank you for walking me through that.
Always ask, please.
Yeah.
So now we want to get all the variables on one side. So let's subtract 6x from both sides, giving me 18 equals 1x plus 16. And then to get the x alone, we'll subtract 16 from both sides. And we'll get x equals 2. But
You have a restriction.
we have restrictions. And the restriction was, oops, was that x cannot equal negative 2.
Hmm.
Well, x equals 2 is okay. And so that should check. All right?
Yep.
Okay. We got a few minutes left, but honestly, I have to say, because you guys weren't asking questions, I'm going on the assumption that what we do, if there are no questions, is all right. And we got a little bit further than I really thought we would today. So let's stop here. What's today? The 23rd. I just got to make note of where we stop. Does anybody